All right, Physics 20 here, your notes on starting in Chapter 7. Section 7.1, the notes are really just on period and frequency, so just knowing the formula T equals 1 over F and F equals 1 over T. Again, how to find those. Okay, if you have any questions on that, just let me know. Okay, but we're starting with 7.2, so simple harmonic motion. Okay, so Hooke's law, okay, is the deformation of an object is proportional to the force causing that deformation. So if we have a spring here and this is at equilibrium at point A here where the spring's kind of just on its own, if we add a mass to it, okay, the deformation, okay, so the X depends on the force. And again, in this case, it'd be force due to gravity. So the 10 grams times 9.81. Well, you don't want to convert that to kilograms. Okay, and so, whoops. So if we double the force by doubling the mass, we're going to double the displacement. Yeah, and so on. Well, it won't, like, I guess it'd be, for each time we add the mass, we're adding the same amount of displacement. Okay, so looking here, so the stiffness of the spring is represented by the spring constant K. We talked about that earlier this year in a different unit. Okay, and the equation we use for Hooke's law is force is equal to the spring constant K times the displacement X. So X is always the displacement from our equilibrium position. So this is where it's starting. That's the spring, like where it naturally wants to be. Okay, as you pull it out, this would be the X value between this line and here. Okay, and then our force applied is going this way. Okay, and so basically for this, the force always wants to pull it back to equilibrium. Okay, and so the force applied is kind of opposite of our force applied is opposite of the force that the spring wants to pull back. Okay, for force displacement graph, the biggest thing to know for this is like the relationship. Okay, as we kind of said earlier, the force is proportional to the displacement. As one goes up, the other also goes up. Okay, and so from that, we can see this straight line. Okay, and then if we find the slope of that line, it's going to give us our K value. Okay, restoring force is the force that's pulling back to get it to equilibrium. So it opposes the displacement to move the object back to its equilibrium position. So we add the negative because the restoring force is always opposite to the direction of the displacement. So for simple harmonic motion, we have a horizontal mass. Okay, this would be at our equilibrium position. When the mass is at rest at equilibrium, there's no tension in the spring, and so there would be zero restoring force acting on the spring. Okay, now at its maximum displacement, okay, its restoring force is maximized. Okay, it's not moving at that state, but its acceleration that wants to go back is going to be at its max. And so the force is at its maximum when its displacement is maximum, acceleration is maximum when the force is maximum, and so okay. And like you have to fill this in your work book on page. Oh, there's a whole page where it just kind of shows these examples, and you just have to state like these. So as it goes back to equilibrium, so it started out here, you let go, it starts to swing back. Okay, at its equilibrium position, its force is equal to 0 because its displacement is equal to 0. If the force is 0, then the acceleration has to be 0. But our velocity is at its maximum. Okay, oops.
Do you like my worm? Do you like my worm, Dad?
Sorry, my daughter came in as I was recording. Okay, moving back to this. Okay, so at the center point, it'll have its maximum velocity. And you can kind of think of it as like, as it gets pulled out, it has more potential energy to spring back. As it kind of goes through at this point, all of that potential energy moves the kinetic. And as it keeps going, it's now pushing the spring in, which would be adding kinetic or potential energy, which cancels out some of that kinetic. So like the kinetic is moving into potential and back and forth. Okay, so max potential over on this side, max kinetic, max potential as it moves back and forth. Okay, so yeah, all the potential energy stored at the spring at the maximum displacement is now in the form of kinetic energy of the mass. Okay, and then as it keeps going, it gets to the point where it can't kind of squish together anymore, okay, which is our negative x value. Okay, and so again, it has maximum force, but now that force is going in the positive, going to the right. Okay, again, if we have max force, we have maximum acceleration, okay, and our velocity is going to be 0. Okay, and then as it returns to our equilibrium position, okay, oh, I missed one. Okay, again, our forces go to 0, and then our velocity is going to be at its max in the positive direction. Okay, so, and then as it continues through, then we get our one full oscillation or cycle is complete. So simple harmonic motion is a acceleratory motion where the restoring force is proportional to the displacement of the mass. A mass on the end of the spring is an example of a simple harmonic oscillator. And for all of these, we're pretending there's no friction that's happening here. There's going to be no energy lost as this mass goes back and forth on this table. It'll just, as we pull it back, it'll continue to go until a force stops it. Okay, in the vertical direction, okay, simple harmonic motion. Okay, for these ones, okay, as we put a mass on the end, okay, it's going to find an equilibrium position. The equilibrium position will be where our F net is equal to 0. So where our force due to gravity is equal to the force of the spring kind of pulling it back to, or like our restoring force. Okay, and so in this case, like our equilibrium is B and D, because that would be where our F net is equal to 0. Okay, if our F net is not equal to 0, if we have an F net, okay, then we'll have a maximum acceleration where F net is max. Okay, and then as it kind of moves forward, we're going to change that. So it's very similar to the on the horizontal, except now like our equilibrium just changes a little bit because we put that mass on there. Okay, and so like an example of this is like your bungee jumper. Okay, experiences simple harmonic motion as long as the cord does not go slack. So as they jump, okay, there would be a equilibrium position. They go past it originally, they'll get pulled up, okay, and then as the cord kind of goes slack, then they'd come back down, passing through this equilibrium position, and eventually when they do stop, that would be that equilibrium position. Okay, pendulum, okay, for simple harmonic motion. Okay, again, the restoring force is like if we think of like this as a curve, the restoring force is tangential to that curve. Okay, and so we need to use our force due to gravity and our angle in order to find the restoring force. So restoring force is equal to Fg, okay, which is equal to mg. So we have to know this mass, and then the acceleration due to gravity 9.81 will equal, or times sine of this angle. Okay, when the bob reaches its equilibrium position, again, our velocity is going to be at its max because like I have potential energy up here. Now it's all kinetic, then it's going back to potential. At this point, this is our, again, like our resting point, our equilibrium point, so the restoring force would equal 0. Okay, now as it continues through, it gets to its kind of maximum height. Okay, again, our restoring force is at its maximum, so our velocity, it's going to stop at that second and then reverse. Okay, velocity is 0, restoring force is at its maximum. Okay, it goes back through, and it's just opposite. And then as the bob is made one complete oscillation, and so like when we're talking about time to or period, one period would be going there and back. So this all the way back to this point is one complete oscillation, one period. Okay, whoops. Moving ahead here. Okay, so the force displacement graph of a pendulum. Okay, so the restoring force, the biggest thing you have to take for this is just knowing this formula. Restoring force is equal to our Fg times sine beta, or sine of our angle. Okay, it changes, force varies almost linear with displacement for angles that are under 20 degrees. If you get over that, then it's going to vary even more. They say even like about 15 degrees is usually our maximum. All right, so you don't have to worry about any of this. You should look over these pages in your textbook if you have any questions, any problems. Okay, there's some practice problems with answers. So like if you can't get one on your worksheet, look at those and you might be able to find the answer there. Okay, but you're working through your workbook, answering all the questions for chapter 7.